All right, welcome everyone to today's installment of our seminar series. And today's topic is risk-based decisions in operation and maintenance. And I'm very happy that we have two of the leading experts on this topic today giving talks and discussing with us. The first presentation will be given by Michael Faber, who is a professor in Aalborg University. Previous to that, he was a full professor at ETH Zurich, and then a dean of civil engineering in DTU, Technical University of Denmark. His research interests are directed on governance and maintenance management of risks, resilience, and sustainability, mostly in the built environment. And importantly, and I guess this will also inform his presentation, is that Michael has throughout his career been working very closely with industry and public authorities, mostly in the field of risk-informed decision support for design and the integrity management of systems, engineering systems. He's also co-founder of a consulting company, Matteo. I should mention that Michael has major present engagements in the Joint Committee on Structural Safety, World Economic Forum, Global Expert Network, Global Risk Forum in Davos, the Globe Consensus on Sustainability in the Built Environment, the Danish Academy of Technical Sciences, and the Danish Research Council. And I'm very happy that Michael has agreed to speak and discuss with us, also because he's my supervisor, so maybe he had to agree, but it's really an honor that you're talking today.
Thank you very much, Daniel, for this nice introduction, and I think you exceeded your time limit for that little exercise.
I'm sorry for that, but your CV is too impressive.
And I think that you have evolved actually long ago to the level that I'm not your advisor or supervisor. It's the other way around. But let me share my presentation. I'll try. Okay.
I still learn from you.
Do you have anything on your screen? Can you see my presentation?
Not yet. You might have to hit enter or share.
Yeah, I actually did that. But I will find it. Just give me a sec. So I'll share again. Yeah. Now it should come.
Yeah, something is showing.
Yeah, and then I'll just press the slideshow. Let's take it from the beginning. Okay. Yeah, so we are in the theme of, so first of all, thank you a lot for inviting me to give this presentation here with Mateo Pozzi. This is my great pleasure, and I'm also honored. I think your initiative to have this series of presentation is a really good one. But let's get going. The theme of these two presentations today. There's a little bit of the theme is on risk-based decisions in operation and maintenance. And what I would like to put emphasis on in my talk today is the system. Of course, I will talk about the other parts, but I will focus a little bit on the system representation as the intersection of decision-making and knowledge and information. Before running off with my presentation, I would like to acknowledge the people funding me, namely the Danish Hydrocarbon Research and Technology Center, DHRTC. This is greatly appreciated. And then, of course, everybody in my research team, my group, and with whom I've been working on these aspects here over the last 5 or 6 years. Thank you, guys. You really did it all. The topics I would like to address with this focus on the system is, first of all, I would like to talk a little bit about the decision context, integrity management. Then I would like to talk about systems modeling in the sense how to represent the decision context. Then I will just super briefly talk about digital twins, fusing knowledge and data. Then I will address how to decide actually. So how do we decide on which might be an optimal strategy for integrity management during operation and optimization of maintenance, namely Bayesian decision analysis. And then comes an intriguing issue, and that is to decide how we identify the best system. And I will talk about Occam's razor, which many of you probably have heard about in many papers. But I would like to try to get a little bit of quantification into this concept. So I will show you some ideas. Then I will close off by addressing best practices in the industry and challenges for research. Why integrity management? Well, we all appreciate that structures and infrastructure systems, they are subject to deterioration processes such as fatigue and corrosion, but also damages caused by more rarely occurring extreme load events. And extreme load events can be earthquakes, as an example. They can also be large waves or extreme wind gusts and many other things. And of course, structures, they can be damaged. We design them only with a certain level of reliability, and that means that there's still space for the events which can actually lead to damages and failures of structures. And we would like to keep control of the structures and make sure that they are safe and they operate as we would like in the best and most efficient manner possible. So inspections and monitoring of the structures and the load environment and also the use in principle of the structures in infrastructure systems, they may facilitate that we can take timely action to intervene operations and thereby reduce consequences if something is going wrong. We can also adequately and efficiently repair damages in the best possible way at the right times, before things become too expensive or before further damages occur. And if we need to, we can also simply make decisions on renewal of structural parts. And we would like to do that cost optimally before risks to personnel and environment and costs are becoming excessive and beyond acceptable limits. Now, in the ongoing demand for sustainability, we also need to be more efficient in general to use less resources and impose less greenhouse gases on the environment. But we also still, at the same time, we need safety for people and reliable structural performances in support of the services of the structures and infrastructure. So this is the challenge, and this is what we do. And this is also what is being done in many industrial practices. And the only available basis we actually have for decision making is information. So how would we like to proceed? And the perspective which we are applying is that we consider the challenge, the optimization problem, in fact, to be an information management problem. So we are representing available knowledge and what can be observed. We are simply considering this to be information, no matter which type of systems, no matter which types of hazards or risks in principle that we are addressing. We just look at it as information, and then we manipulate the information. And this is a basis for the decision making, how best to manage the information. And we can do that by collecting information. We can do that by changing the physics so that the information actually is changing. And here you might look at the value chain of information from it's being collected and till it supports decision making. So if you look at the right-hand side, we have the structure. We can put on monitoring devices, or we can make inspections. And the events of the state of the structure is what we observe, and we transform that to what we normally address as data. And the data we try to relate somehow to information about states of the structure which are of our main interest, states which are of our concern for the decision making, and we interpret these as indicators. So we might measure an acceleration on the structure, but we're not really interested in the acceleration. We are interested in possible damages which might affect the dynamic properties of the structure, which we can actually understand if we look at the accelerations. And that provides the basis for increasing our knowledge. We combine that, of course, at all points in time with our experience from past observations and past projects of similar kind, and that supports decision. And then it leads to actions which manipulate the reality which we are monitoring. So it's a circle and it's a value chain. But in all points, in all links in this value chain, there is a possibility that information may be associated with errors, so it can be disturbed. Links can also be broken in points in time and picked up later. There can be several things to be concerned about regarding the information. Here, just another example, just to let you know that we are not only looking at offshore structures, but also bridge. Here, we are looking at stay cable supported bridges in the context of ice accretion and the possibility of dropping ice on the vehicles. And the idea is that we observe environmental conditions. We relate environmental conditions to event of ice accretion, and then we combine in the end our observations, our model relating weather conditions with ice accretion and dropping ice. We combine that with forecasts on weather conditions, and then we have an early warning system. So this is a very clear-cut and very interesting case which is being applied also. So when we look at the information, it's useful to look at a broader classification of information states which are interesting, and that is that the information could be relevant and precise. So it's actually the information we need, and it's precise, no uncertainty. The information could also be relevant but imprecise, and this is what we normally do, and this is what the focus is on in our field, and or it could be biased as well. Incorrect, I denote that. And biases are generally not accounted for in what is going on in inspection and monitoring supported risk assessments for the purpose of optimizing maintenance strategies. So this is something which we are working on right now, but much more need to be done in this domain. It could also be that the information is irrelevant, and that means that the information we are picking up has, in fact, not very much to do with what we are really concerned about. And this is actually something which is important to realize. There could be different systems which could explain the observations that we are making and collecting through inspection and monitoring. And of course, as I said, the information can be disrupted and delayed. So monitoring devices can fail, and they of course also do that. And maybe sometimes slowly they degrade, and then we don't notice it if we don't have a focus on it. We have to, so the general perspective is that in principle, we don't really know the systems, the structures, infrastructure systems, the monitoring devices, and so on. We cannot claim that they are known. We have a good idea about what they are, but in general we don't for sure know. And there may be, and in general, are competing possible systems which are explaining what we see and what we observe by devices and instruments. And in principle, all possible systems have to be accounted for. And this is a little bit something which is missing, because we tend as engineers to think that there's just one model world. The model we have in mind looks like what we saw on the blackboard when we were going in school at university, and this is how the world really is. So we omit the fact that there could be different explanations for what we see. And also the information flow and effects of information, they really have to be explicitly accounted for as a cause of adverse consequences, but also as a means of management. So if you're looking to the system modeling framework, this is the one from the Joint Committee on Structural Safety. We have the real world in the right. We are observing the real world at, let's say, different levels in the modeling framework, at the level of exposure, vulnerability, and robustness. And we can make decisions in order to control the risks as, in the system at the exposure level, vulnerability level, and robustness level. So we can take action which are controlling the risk at these three levels, and this is generally what we do. And we are modeling the performances of the systems in terms of systems analysis, where we look at how hazards can affect the system and how the system might change in itself. So it might find an equilibrium, even though it's damaged, but damages can also be so big that the system we're looking at is no longer able to redistribute internal demands in the system, and that could lead to a total system collapse. And this can go for a roadway network. This could be relevant for a structural system. So this is more or less, let's say, a more generic type of system perspective, which should be taken. And then the probabilistic representation of the system. What is important to identify are the scenarios which are actually leading to consequences, and the consequences can be in several dimensions. So it can be consequences associated with cost, damages to the environment, or let's say loss of lives or loss of health. And these scenarios we can model probabilistically. And without going into any detail on how this is adequately done, we are working with the machine learning and the Monte Carlo simulation on how to efficiently identify scenarios. This is just one way. I think there could be others. But in the end, we will end up with a probabilistic system model where we have, for each of the scenarios leading to consequences, we have their probabilities of occurrences, and we have the direct and the indirect consequences associated with the scenarios. And we split the direct and indirect, the direct consequences into what we call initiating consequences and direct propagating consequences. As long as consequences are associated with damages or failures of individual constituents of the system, we denote them direct. And as long as the consequences are associated with loss of functionality, we denote them indirect consequences. Doing this, we are able to split them up into direct and indirect in the different phases of the progression of the scenarios, and we can evaluate the indices of robustness, and that gives a good decision basis also on how best to manage the system, how best to take action depending on what we observe and monitor. Now, I just want to highlight the general system model representation. So if you imagine that we can develop probabilistic system models let's say in the format of Bayesian probabilistic nets, you realize that we are operating with structures. That means a set of variables which are interconnected by links, edges, we call them. And we can identify these based on either, let's say, bottom-up or top-down approaches, bottom-up traditional engineering or top-down machine learning related techniques. We can identify these structures. But in many cases, when you actually do this, and you do it on the basis of data and prior models, you will end up with alternatives which could explain your experience and could explain the available data. So in principle, there are a manifold of possible structures and associated variables. Of course, many of the variables will be the same in the different structures, but in some of the structures, some variables will be missing, and in some of the structures, the edges will be different. So here, just for illustration, I split it up into the graph model sigma and the constituents models C, and the probabilistic models for the variables entering into the constituent models X. And then, of course, decision alternatives, they have to be represented in the system representations. As I said, bottom up, top down, in the end, it's mostly adequate to look at the combination of these two techniques. I think I have to speak much faster. Digital twins. Well, digital twins, I would like to talk about the probabilistic digital twins. So if we have the model, as you see in the left-hand side, the starting point, this is really the model that we can formulate based on experience. And then the system which we are addressing in reality might be the one, I'm sorry, I said right, I meant in the left side. This is the model, and in the upper right corner, we have the real world. And by combining, let's say, simulations based on our model with observations from the real world and doing data mining exercises and then discrepancy model, we may be able to adjust our model universe in such a manner that we get the best agreement between the data that our model universe can generate relative to the data we have observed from the real world. So this is one way of building, let's say, probabilistic twins. Not just twins, but probabilistic twins, which is a super useful concept. The base, when we have the system, when we have established our models, and including the competing models, then we need to make decisions. And we have the prior decision analysis, we have the posterior decision analysis, and we have the pre-posterior decision analysis. I just want to highlight here that the prior decision analysis really takes basis in a risk evaluation, because the expected value of utility we normally associate in most cases with expected value of life cycle cost. And this is nothing different from the probability that cost will occur, and then the actual cost if they take place. So this is just expected value of consequence, and this is so this is what is to be understood as risk. And when we have new information about the system compared to the starting point, then we use Bayes' rule for updating our probabilistic models. And Bayes' rule is really the key. Here in Bayes' rule, we have the prior knowledge associated with these, the density with one prime, and in the denominator, and we have the L as the likelihood in the denominator. And the likelihood is the important thing here, because this is what carries our observations into the states of the system which have our interest. And so this is where the inspection quality comes into the picture. This is where the information collected through monitoring comes into the picture. And you see here that we need to model this likelihood. And traditionally, observations are considered to be independent in these Bayesian updating. So you make one inspection and get one observation 1 year, and then you get another one the next year, and you assume that they're independent, and then you use this information independently. But in reality, very often they are strongly dependent, and so you somehow overuse information. You use it twice, maybe sometimes. So we have to be very careful on that operation. The pre-posterior decision analysis is a tool which we can use for planning future efforts on inspection and monitoring, and we do that using the principle of value of information, which I think Matteo will talk much more about. I'll just show you this slide here to let you know that we also have the formulations where we can account in the decision making for possible different competing systems. And we are also able to identify the robustness of the decisions which we derive from a, let's say, multiple systems decision problem. So if we can immediately, let's say, evaluate and compare how sensitive our decision basis is for the possible event that the final optimal solution is based on a system which is actually not occurring, is not there, but another one is there. So the overall approach for integrity management we have here in this figure, which is broadly adapted from the TU 1402 cost program, where the flow of information is indicated. I will not go into the details. I'll talk about Occam's razor because you all appreciate, or many of you appreciate, that when we formulate probabilistic models and also competing probabilistic models, there are, of course, many different possible model choices. So we need to address the problem, what is the best system representation? And this is normally decoupled from the decision problem. Occam was a priest in the period end of the 12th century to the end of mid 13th century, and the idea is his point was that whenever we are addressing some sort of complex or trying to explain some sort of complex phenomena, then the explanation which involves the least number of assumptions should be preferred. And this principle is being referred to in science everywhere, and not least in the health monitoring science. But nobody so far I have seen have actually tried to let's say challenge this principle. So we can always go for simplicity, but when is it oversimplified, right? So it can also be oversimplified. We need to find the right balance. And normally we use principles as maximum likelihood methods or the max a posterior probability expectation, or we use, let's say, measures like traces of the invariance of the information matrix, or things like that as a means of identifying a good model. But such models are totally separated from the decision context, and the coupling to the decision context actually, I think, is the key to identify optimal models, and this is also key in maintenance planning to do that. So just for the super simple case where we have a concrete cube under stochastic load L, and we want to optimize the cross-sectional area of this cube, or let's call it a short column, and we have a probabilistic model. In this particular case, we have a probabilistic model for the concrete compression strengths, and we have imagined that we have simulated some outcomes of this, and you see in the figure in the histogram, you see that the concrete compression strength is represented as a histogram, established using, let's say, the traditional rule of thumb on intervals of the bins, the bin width, and then we have the load just plotted up. And now we would like to optimize the decision on the cross-sectional area, accounting for the cost CD, which are 1 unit per 1 unit of area, and then the cost of failure, which we assume are a factor 100 higher. So we want to minimize the cost, and we can do that by incorporating the choice on the probabilistic structure describing, so the histogram. So now we are searching for an optimal histogram instead of using the standard approach, which we normally would do, right? And what you actually see here are the two histograms. So on the left-hand side, you have the traditional one, and on the right-hand side, you have the optimal histogram. So this is your optimal probabilistic model in the context of this particular decision problem. And when we do these, let's say, optimizations, what we, of course, do is that we account for the model uncertainty and we account for the statistical uncertainty. And this is how these bin risks come out of the picture. Looking at best practices in the industry, in the oil and gas industry, whether it's fixed structures or floating structures, these risk-informed approaches, they are significantly applied. This is a high-risk industry, and they realized at an early time that it's a good idea to get control of damage developments. The aeronautical industry, it's the same thing. We don't hear too much about it. Most of it is done in-house. In the bridge infrastructure system sector, it's used. I have been involved in a couple of projects, but it's rarely used. Considering the amount of structures which are out there, it's definitely an area which should be lifted. And building structures, it's even less than hardly used. In the wind turbine industry, it's emerging. So risk-based approaches for inspection planning are being used by a few operators or owners. We are now in the process of coupling this up with monitoring in order to sharpen the risk-based inspection planning strategies. The bottlenecks, I think a lack of understanding of what risk is, also understanding that a risk associated with the future operation is actually equivalent to out-of-pocket losses in the present moment. This is hard for people to understand, and because of their, let's say, short period in the different functions in public authorities and in industry, they don't care too much about what happens in the future, the risks, but they focus more on the expenditures, let's say, this year and the next year. Also sufficient training of personnel, of course, that's related. This is much to the, let's say, the loss of the, or to be blamed by universities or on universities. And then also something which is maybe for us to be blamed of, lack of adequate tools for risk-based operation and maintenance planning. And also the facts, and this is maybe the main problem. The construction industry is driven by a very highly competitive market, which has a strong focus on price, cost, time, and simplicity rather than always doing better. In the research domain, as I indicated before, my presentation of systems and the modeling of dependencies in inspection outcomes and the data which are collected through monitoring. This is something we need to address a bit more carefully. And then a consistent integration of risk-based in inspection planning and maintenance planning approaches with the information we can get in from structural response monitoring or load monitoring. That needs to be improved, and the tools correspondingly, of course, also. And then there's the issue of portfolios of structures. How can we utilize inspection results, or even better, monitoring results from structure to structure, or from infrastructure system to infrastructure system? That also needs to be much more carefully addressed. And finally, the further development of tools. And here we see a strong and very rapid development of tools from the area of machine learning and artificial intelligence, which we are employing, and they need to be utilized, of course, much more. That's the end of it. Thanks for your attention. And I look forward to some questions, which I understand will be in the end, right?
Yes, that's correct. So thank you very much. We would first continue with the second talk by Matteo, and then we'll take all questions in the end. So with this, I would like... Yeah,
sorry to interrupt, because I forgot to say at the beginning that you can type at any time your questions in the Q&A. So put your questions there, then we'll pick it up later.
Yes, I mean, you can already write as, you know, a question pops up during a presentation. That would be helpful also for us for sorting what questions to ask in the end. Maybe with this, I proceed to the presentation, the second presentation for today, which would be by Mateo Pozzi, who's an associate professor in the Department of Civil and Environmental Engineering at Carnegie Mellon. Matteo received his PhD in structural engineering from the University of Trento and was also spent a postdoctoral research stay at the University of California, Berkeley. His research focuses on probabilistic analysis, risk analysis tools, and hence you understand also maybe the presence in this tandem workshop, applied particularly to civil infrastructures. He has worked with integrating fiber optic sensors and using wireless sensors for measuring strains and vibrations, and coupled this work also with tools for reliably mitigating risks and extend the remaining useful life of civil engineering structures. He will be, his group focuses on probabilistic models for seismic vulnerability, deterioration, optimal planning for mitigation of extreme events, and maintenance and inspection scheduling. And I believe he will be focusing on this today. So with this short intro, Matteo, the floor is yours.
Oh, thanks a lot, Eleni, for this very kind introduction. I'm trying to turn my video on, but maybe Antonis can help me doing that. I think I need some authorization.
I thought I had it, but
okay. Now it's perfect. Yeah.
Yes, it works now.
Okay, this is the wrong camera. It's fine. All right, and thanks, of course, to QM, the Institute, Eleni, Daniel, for this very kind invitation. It's really a pleasure to be a speaker in this seminar. Let's try to change camera. Okay, that's better. Great. Can you see my presentation?
It's not yet full screen. If you want to,
I see it.
Okay, now it is.
Yeah.
Okay. Thank you. Thanks. Yeah, I think it is definitely hard to follow Professor Faber's great inspirational presentation. What I prepared today is still along some similar line of trying to integrate in information with decision. And so the overall vision from the standpoint, for example, of an infrastructure management is to model the physical world with some numerical tools at the level of the entire system and of different components, and then interact with the physical world, doing actions and receiving revenues, but also information. So actions can be retrofitting a component, but they can also be exploratory actions. For example, inspecting a component, receiving data, installing a permanent monitoring system, or doing an experiment, or even try new technology. So overall, we are dealing with some possibly deterministic, but at least partially unknown to us world. And we can use a probabilistic framework to model what we know and what we don't. And overall, this optimal behavior is an interplay between some long-term prediction that we refined by processing more and more data, including the prediction of what would be the effect of our action. In this, and in planning for exploratory action, as Professor Faber says, a key concept is that of value information that also is mentioned in Professor Faber's slides, is related to the seminal work of Raifa and Schleifer from the early 60s. And briefly, even I know that most of the audience are familiar with the concept. I will give a brief introduction from my standpoint of what the value information is. So say that you have a component in some uncertain state, and you can take an action and you have to pay a loss that is a function of this state and action. But before you take your action, you can get some information that hopefully allows you to better take your decision. So if you want to assess what is the benefit of this information, first of all, you have to solve through Bayesian inference, the inference process. You have to infer for any possible value of this observation what you know about the condition state. And then you have to assess what is the corresponding loss for any of your action, and you have to optimize your action. And this optimization is the second layer of complexity. And then you have to assess what the optimal loss would be for any possible output of your source of information. And when you compare this expected loss with a higher prior loss, you get the value information as a difference, as an expected reduction of loss. And this will quantify the benefits of say, installing a sensor or permanent monitoring system. And then you can even try to optimize this information gathering campaign. And if you do so, you have this additional layer of optimization that makes, in general, the entire picture pretty complicated, because it is an optimization based on an integration, based on an optimization in turn based on an inference process. However, if you're able to do this computation, you have a very interesting feature that is, again, the benefit of information. So in a very, very simple application, say that the component is binary, so the probability of failure from 0 to 1 define the state of the component, and if you do nothing, the risk is linear from 0 to the failure cost. But if you repair by paying a fixed cost, you can eliminate the higher risk. So this lower envelope between these two linear functions is, you can call it the prior optimal cost. And this is also related to this optimal policy that tells you, in this case, do nothing up to this threshold and to repair after that. And if you consider that you can take perfect information before you take your decision, in turn, the loss that you're going to pay is this linear function plotted in blue. And the difference between the two is, in this case, the expected loss of perfect information, that, as you see, is 0 when you know already that the component is perfectly intact or is perfectly failed, and is going up and down in between where there is some value. And instead, if your observation is imperfect, your posterior loss would be somehow in between, that with perfect information and that without information. And correspondingly, you have this value information that is less than that's related to perfect information, but in this case has a similar shape. And you can easily generalize that to the case of multiple actions. If you have 3 actions, well, the optimal loss function would be the lower envelope of this, sorry, in this case 4, you have the lower envelope of these 4 functions. But because it is always the lower envelope of some linear function, it is concave and continuous. And if you have access of information, you can base your decision on information, and this creates these additional linear functions that are related to some adaptive actions, the idea of reacting in some way to the output of a sensor, let's say. And because these create, again, additional, say, conditional plan, you're able to define another lower envelope of these new functions, and you can call this the posterior optimal function, that will be as well concave and continuous. And moreover, because you are more flexibility, listening to the sensor, this posterior loss will be always less or not higher than the prior one. So now you can define the expected value of perfect information as the difference between the loss with perfect information and the prior one, and the value information as the difference between prior and posterior loss. And, it's kind of interesting that you can see this posterior loss as a kind of a smoothed version, a kind of a moving average version of a prior one. It is because when you get information, you're moving around, your belief is changing, and you're kind of taking an average of a prior loss. So pre-posterior analysis, also mentioned before in the previous presentation, can be seen as a kind of a trade-off when you are ready to give up your prior belief for a lottery, when with specific probability, you get your posterior belief. For example, the probability of failure can go up or down when you listen to the sensor. And by Jensen inequality, it is proven that it's always profitable to trade your prior belief for the uncertain posterior one. And again, the value information is this different, so it's guaranteed in this setting to be non-negative. The previous case was for a binary system with just two components, so your belief is defined just by one number, say probability of failure. If you have a free state system, instead the domain of beliefs, instead of being a segment, would be this triangle. And similarly, on this convex domain, you have, in this case, different planes related to the different actions, and their lower envelope would be your optimal loss. For dimension 4, you can still visualize how the belief domain is a tetrahedron, while you can't visualize much for dimension higher than 4. But of course, that doesn't mean that computationally you cannot handle much higher dimension than that. So value information is a key for many arguments and many possible decisions that you can take. In case of exploratory actions, for example, sensor placement may be related to the optimization of value information. You can argue that the best configuration of a sensor is that minimizing the posterior loss or maximizing the value of information minus the cost for that. Now, in the domain of collectible information, maybe in time and space, you can assess this function for all possible combination of, let's say, of sensor networks. But of course, this exhaustive search will be very demanding because of what is called combinatorial explosion in how, the different arrangement for the sensor networks. However, there are proposed traditionally efficient algorithms to deal with the issue. The idea of a greedy algorithm is to place a sensor in the best location as if you have access just to one sensor and then add another one and so on. So the number of combination becomes much smaller than that, kind of grows just linearly with the number of sensors. Of course, you are suboptimal, but in many cases, what you observe is that you can get pretty effective results by following this optimization. And generally, what happens is that the value information is going up when you are considering larger and larger systems, because larger and larger sensor networks, because you are collecting more and more information. However, the information is more and more redundant. And so you have kind of something similar to the law of diminishing return, so that the marginal benefit of adding a new sensor generally is less. And again, when you include also the cost, theoretically at least, you can optimize the network, avoiding over-instrumentation. And this, again, it is true in many cases. Actually, you have this issue of submodularity that unfortunately you encounter for value information. And when that happens, even the greedy optimization is not really effective. So this is an example of a few years ago, a publication related to optimizing sensing networks for seismic risk in the California area. And, it's honestly a bit a simplified approach. But again, you see the same trend of a lot of benefit when you start instrumenting few components, and then you have less and less benefits when you go on upon that. So more recently, we are working with Junho Song, and Chao Lin is a PhD student, on the idea of understanding what is the best component to monitoring in a system in the traditional sense. And in this case, basically, in this setting, you have a binary system, an origin and destination, and you need to understand what component has the highest value. Think, rightly so, that bottleneck maybe more important because of a role, but actually it really depends by the specific setting that you're using. In this paper, we are proposing something called a global matrix based on essentially on the system probability of failure, and a local metric that is instead more related to the actual maintenance cost. And this is just to show you how there's a difference between the ranking proposed by this that is, for example, the cost for repairing the different components. Of course, this has an impact of the order, and different components may become less or more important for inspection, depending on these parameters. A general rule that we have found out is that if you look at the global metrics, that is again related to this probability of failure. So this graph is very similar to something that I showed you before. You have probability of failure on the x-axis and loss on the vertical axis. So for a general system, again, you have your prior loss, and when you are considering inspecting a component, your posterior loss can go up or down. So when you're considering two components to understand which one to inspect, you can argue that for this very special case of binary observation, if this posterior interval showing you where the posterior probability of failure is going up or down, depending on the fact that you hear, say, a silence or an alarm, if this is bigger than the interval for the over component, then this component is more important, no matter essentially what the loss function is. This is something that we proved, and a bit kind of very simple application for a serious system. In this questionable setting, you should always inspect the most vulnerable component. In a parallel system, instead, you should inspect the most reliable one. So this is just for the static case where components is included, and then value information can also be formulated for sequential decision making, where information are taken in a sequence, like playing chess. But of course, here the application would be taking care of an infrastructure system or component. And as Costas and Jenny wonderfully explained in the last seminar, this can be addressed by this setting of a partial observable market decision process. It's a pretty computationally expensive but very general setting for dealing with this problem. And in this context, instead of dealing with a loss function, you have what is called a value function that accounts for the expected long-term cost until the end of time. And in this context, you can define different concepts of value information. Something that we defined in the past was this, well, first of all, we focus on the value of current information. The idea, suppose that a component for a long time, but right now you can say inspect the component. What is the benefit of inspecting the component right now? Now, this would be the value of current information, and it turns out that this value depends on the specific, on many things, including the specific assumption that you're doing about the viability of future information. If you don't inspect right now, when would you expect in the future? So the pessimistic assumptions say that you will never inspect it in the future. And this allows you to compute a specific value. On the contrary, the optimistic assumption, this is just our pretty naive definition, is related to the fact that future. So with this additional, with this alternative assumption, you can define another value of current information would be different. And this shows that the value of inspecting right now is highly related to what you do in the future. And then you have the value of flow of information, that is the value of installing a permanent monitoring systems. And pretty recently, we have discovered that there is a formulation that allows you to express one as a function of the over, meaning that you can express the value of flow of information in terms of the value of current information. So the idea is that think that you have this kind of somewhere on your belief, probability of failure, and in time, this frog is randomly jumping because your belief is changing because of observation. Now you can think that jumping around, this frog is cumulating the optimistic value of current information, and when that, it obtains the value of flow of information. So kind of intuitively, even if the details are not maybe completely intuitive, at least to me, it turns out that you can express the benefit of installing a monitoring system as a combination of the value of getting any single observation at any time. Yeah, so this is just an application from another pretty recent paper, and this shows for application of a very simple structural system, it shows you how the value information is going down with the inaccuracy, with the error, kind of intuitively, the more noisy or inaccurate your measure are, and the less the value information is. While the other graph refers to the impact of your prior precision in predicting, let's say, where the failure would be. So in this case, what happened is that if you're very precise in predicting what the failure would be, even without the monitoring system, there's not much value. But if you're less and less precise, there's a higher and higher value. And of course, this is kind of intuitive, but be aware that mathematically, this is not at all guaranteed. That previously mentioned issue of submodularity tells you that sometimes information has a high value only in conjunction with another piece of information. So sometimes installing a monitoring system maybe is very relevant only if you know something else, but essentially not in this case. And in this, another analysis that we have done is related to what I told you before of what component to inspect, for example, in a parallel system. We have seen that in the one-shot static case, you should inspect the most reliable component, and that maybe see, I don't know, sometimes even a little bit counterintuitive, that you should inspect the component that you think that is the best one. And here we see how this actually changed when you put time into the picture. When you put time into the picture, so the blue component is the most reliable one, and it's kind of true that if you don't care much about the future, here you have a low discount factor, you should inspect the most reliable component. But if you care more and more about the future, you should focus your attention on the most vulnerable component, even in a parallel system, because essentially you try to preserve some redundancy. So the last big topic that I want to mention is that of information avoidance that I worked on in the last few years. Information avoidance is this idea that sometimes you prefer not to know. And this is a song recommended by a colleague of mine, by Toby Cave. Let's say, I wish I didn't know now what I didn't know then. It's a very sad song, but it gives an example of why sometimes we prefer not to know. But our interest actually was pretty different respect to the context of a song. We are interested in a context where maybe manager of some infrastructure system, they prefer not to install a monitoring device because they think that with the monitoring device, they can be charged because of some liability. And so in some sense, they think that not knowing is better. Now, to understand this phenomenon, we have proposed this pretty simple setting where, again, there is an agent that is forced to obey an external regulation, let's say reliability-based regulation. And for example, let's say that society has a very high cost of failure. And because of this, society force a very stringent policy. Let's say that you have to repair even when the probability of failure is relatively low. Instead, the agent will prefer to take a higher risk because for the agent, let's say the cost of failure is less. So in this sense, the agent is forced to follow a policy that is not optimal. And if you remember also last time, Jenny and Costas mentioned the fact that when the policy is not optimal, there's no guarantee, for example, that the value information is not negative. So in this case, this would be the loss function for the agent. And again, the posterior loss function is a kind of local smoothing of the posterior loss function. And now you can see that, for example, here, the posterior loss function is higher than the prior one. And that means that you have a negative value information. So you prefer not to know in the sense that if you, even in the expected sense, if you install the monitoring system, your loss is going up, and so you're losing utility, let's say. While, of course, the unconstrained value information, as before, is guaranteed to be non-negative. So I briefly mentioned that this, of course, can happen exactly in the same fashion also in sequential decision-making. So pretty recently, with one of our students, we work on just extending the idea from one shot to sequential decision-making. The idea is essentially the same. Now you're working with value function, so long-term cost, society is forced you to do something, if you can inspect, let's say, just collect information right now, you can have a negative value of current information. Again, if you can repeat the analysis for the optimistic value of current information, and you always find out that that can be negative. And because of what I told you before, even the overall value of a long monitoring system can be negative. Because, you know, in some sense, what happened is that this frog is jumping around, accumulating negative value of current information, and because of this, you have a negative value of the flow of information. So again, in a nutshell, with external constraint, you can get a negative effect of information. I don't think I have really much time to cover much this over topic, but I just want to mention that this, of course, can be also covered in the broader topic of game theory, where you can think that you have different agents like society or manager, or maybe two owners that for some reason they are not in perfect coordination. When that is the case, you have to deal with cost metrics that report, again, different costs for the different agents. In this very simple setting, you have binary decision for one agent, binary decision for the other, and you have different costs for them. And now you can put some arrows that define what would be the conditional response of any agent respect to a decision of the other agent. And when, like in this case, you see the two arrows pointing in the same cell, you have what is called a Nash equilibrium. The idea that a pair action, each of them is optimal respect to the action of the other agent. And now, first of all, we in order to understand what is the effect of information in that, we ask, well, how many equilibria you may have. It turns out that you can have none, unless the pure equilibria. You can have just one equilibrium, and that is very, very good for predicting what the behavior of the agents will be. Or you have multiple equilibria, for example, agent that say, I'll repair only if the other guy will do, or I repair only if the other guy won't do. You can have in series and parallel system this kind of setting. And these, of course, make a little bit more harder to model what the behavior would be. So just one slide before the conclusion, some very preliminary result of this work that is done with some colleagues in computer science, Nia Balkan and Avram Bloom, and Chao Li, our great student. Think of, so a very simple case that you can think of is like this. Say that you see these arrows are pointing in the same direction to the right. No, sorry. The vertical arrows are pointing down after the alarm, after the sign. So no matter what the sensor will do, you know, agent number one will always repair. If that is the case, turns out that it can be proven that for agent number two, for the other agent, the value information will be in a negative, but for the first agent that will always do the same thing, that can be actually negative. Also, the same setting of society and agent can also be reshaped. Now, instead of having hard constraint, we can think of agent one, society, recommends an action, and agent two that has to pay a very high penalty if the agent is not following society recommendation. And that happens, you can have, again, the same setting that I showed before. And lastly, you can have, think of a system where different components are managed by different agents. Again, here, you can again find out that depending on the setting, you can find out cases where the value information is negative. Maybe at least some of the agents prefer some of the components not to be inspected. And why? Well, because overall they are in the expected sense, you know, in a better shape without the information. So this is all my presentation. Just to summarize, I think value information is a great tool, very powerful and fascinating to me tool. It can be, the analysis can be very complicated, very complex, and depends on the specific details on the loss and the uncertainty. For sequential decision making, QMDPs is a great tool, again, very complicated computationally, but very powerful. And there is this nice relationship between information and kind of geometry of a loss function, so that guarantees some property of a value information. And when you have multiple agents, this property can be violated. And game theory, again, is this even broader setting for dealing with multiple agents and in game theory, you can have a pretty complicated attitude towards information. That's all. I need to thank all the students, Milad, Carl, Shuo, and Chao Chao that has worked in the past and working now on this topic, and support for NSF, of course. And that's all for today, except for the great question that I'm waiting for. That's it.
Great. Thanks, Matteo. Thanks, Michael, both for the very inspirational and very interesting talks. And yeah, now we have ample time for discussion, and everybody is welcome to put questions in the Q&A, or if you want to raise a question live via audio, just let us know and we can also allow you to do that. Maybe since there is a question posted here to Michael, maybe we will actually start with that and then go on. Yeah, the question here is how do we introduce model fidelity in the concept of the probabilistic digital twin? And and then I also have a follow-up question from my side, which is, but maybe let's first look at this specific question.
Yeah, thanks for this good question. Well, by model fidelity, I assume that you mean the refinement in the modeling. The sensitivity of the modeling, and that fits straight in to the probabilistic modeling. The closer we come on average, and not only the average, but all the probabilistic characteristics of what can be observed from reality, the better representation we have, right? But if you also combine, and I guess I was having too much on my plate in order to get all the ideas across, because when you look at the problem of developing a digital twin, then a key issue, coupled with all what Matteo just told us or explained to us, the key issue is to use the available and the achievable information potential best in the context of the decisions that we are trying to support through the information. And that means that an optimal, so let's say a traditional probabilistic digital twin would be the histogram with equal bin width, right, along the line of possible realizations. But the optimal probabilistic digital twin might be a very, very good representation, for instance, in the lower tail of the capacity probability density distribution, and then something which looks like nothing from nature in the other parts. So we only need digital twins to be good in the domains where it matters for the decision making. And of course, I think you probably come out of structural digital twin, let's say theory and methodology and techniques with your question, but it is basically the same answer. That of course what you're doing fits directly into the framework, but my point is that we don't just want to look at one let's say deterministic resemblance. What we really need in order to support decisions is that we propagate the resemblance in a probabilistic manner. So what we need to compare, what we need to achieve is a high fidelity in the probabilistic characterization in the corners of the twin, which matters for the decision making.
Yes, but maybe this brings me to a follow-up question, which is, since we often dealing with risk and reliability, and so what matters for the decision is really kind of often outside of the data that we actually observe. So typically we have our models, we can learn them or update them with the data as you showed. If we have multiple models, we can even do model selection, but very often in risk and reliability, we are somewhat outside of the data.
Mhm.
This is a challenge, no?
This is what did you call it? A chance or
Challenge? Well, a chance for.
Yeah, well, but when we do these modeling, when we do the modeling, when we do the knowledge representation, we of course we have to be careful to not let us be pulled around too much by the data. So at all points in time, we need to keep in mind what our prior knowledge and understanding of the phenomena that we are modeling, what they can tell us, right? And that should definitely be included in, let's say, as a constraint for the utilization of what we observe and use to as a part of establishing our model. So it's not only data. I would be very careful in circumstances where we only have data. I would always have a focus on getting the physical understanding into the picture, and there, let's say, the extrapolation. So the predictions into events, which are so rare that we don't observe them, we do need to include, let's say, the available physical knowledge on these extremes, right?
Maybe if I could ask a question for Matteo, because you know, whenever you want to plan a policy or some sort of strategy, you sort of have to forecast into the future, and it's the same also for risk-based analysis. And there's a number of assumptions you have to impose there. One of the main assumptions perhaps being the evolution of a deterioration mechanism, the probability of a sensor failing, the probability of an extreme event occurring, all of which are of course uncertain and not necessarily characterized robustly, as Michael mentioned, by our models, our assumptions. Do you think that, first of all, how would we cope with this? But do you think that there's also potential for monitoring and observations over time in case we become better at, you know, monitoring more processes to fix this or to provide a solution to this?
Mm-hmm. No, you're right. Absolutely. This is a great question. Let's see. I think you're totally right that I think we are aware of that, right? We know that the ingredients that defining our model are, for example, probability of some change of state, referring like to a temporal model, or these emission metrics that define the relationship between the hidden state and the observation. And we know that.
But even, you know, the Markov assumption is not necessarily
right.
correct. Yeah.
Yeah, right. Again, yeah, but yeah. Well, I mean, it depends what is the state, right? I suppose one say, well, if I put the entire word in the state,
yes,
I mean, Laplace thought that it was Markov. Yeah, but so I think that you're right that we also understand that we can put everything kind of back in the state, but this computationally make things horrible, and there's a huge cost to pay if we want to keep consistently the emission metrics uncertain, or the transition metrics uncertain, and so on. And most of the time we say, oh, we just put this some expected value and everything will become much simpler, but maybe we don't really analyze how things will change if we were more honest and put things more consistently, just because it's computationally very challenging to do that. I think, you know, so in the past I've tried to do something that is a little bit suboptimal, but is based on some kind of myopic approach in which maybe you try maybe different transition metrics, different emission metrics by sampling, and you greatly you take the so myopically, you take the optimal decision that is good under the sample. But yeah, it's just kind of a numerical technique. I think your question was much broader than that. And overall, I think that, so I mean, at some very abstract and useful level, we know what it should be the right way. We can just put everything in a gigantic model. But the trade-off between where to make simplification, it is an art, and I can't claim at all that I'm such an expert of assessing what is, the hardest kind of simplification to make. Right? It is better to think that the sensor will not fail, or that we know the degradation. I think that everybody has a cost, some sense in terms of suboptimality, but I can't really. My expert knowledge does not allow me, honestly, to understand what is the hardest issue. But yeah.
No, I agree. I just hope that, the collection of more persistent or more continuous information will somehow yield benefits in this respect.
Well, definitely. If you put everything in the state, the uncertainty that you have on the performance of a sensor will go down because you have observed more and more what the sensor will do and so on. But yeah, it's still very hard. Yeah.
Perhaps not to put our panelists on the spot, but in fact, we invite also further speakers of the series to join the panel, and that's why you also see some of them here in the screen. So I don't know if there's questions from our panelists.
Yeah, actually, I do. Hi, Eleni. Hi, Daniel.
Hi.
Michael and Matteo, two great presentations. Michael, I especially want to thank you for this presentation, because in my presentation next week, I was going to get into the details and challenges of the digital twin approach. So what you have presented today sets a great stage and foundation so that I don't have to, I can skip all those slides and be within my time limit. So thank you so much. Matteo, I have one question for you, which is, if you have multiple agents that are multiple decision makers, now quite often what happens is that not all the decision makers are fully aware or have all the information that they need to make the decision. So they have partial information. So that creates a lot of complications. So I don't know if in your case, because when we do game theory, we can talk about both the players having complete knowledge about the other person's moves, or only partial knowledge, and then of course uncertain knowledge. So do you address that issue at this point?
No, obviously not at this point. No, they have uncertainty about the state of the components they're going to respect, but what is the utility function of the other players? They know that. So definitely, you're totally right that game theory has been, well, in this, especially also in this pretty, simple way that I presented, has been blamed of being kind of too rational, because, okay, you have to assume you know what the other player wants, and also, an infinite loop of recursivity about knowing what the other player will know. The people that we are collaborating with in computer science, they are used to algorithms in algorithm game theory, and there is of course some even pretty simple algorithm in repeated games, where you just assume that each player will assume that the other player will repeat the move done in the previous round, and of course that will greatly simplify. But for the moment, we try to consider what would be the Nash Equilibrium under this kind of perfect information about the utility or the cost metrics. Because again, our focus is mostly about the uncertainty about the state of a physical system. Yeah, if God wills, we will also try to include this over uncertainty, but as you say, it may be pretty important.
But in reality, it's not only. It's an old thing. This information symmetry, let's say, condition. it's actually much more complicated because in reality it's the perception of symmetry. and that so depends on the sequence of previous moves, and all the prior experiences of the players come into the picture here, as well as personal traits. So it's super complex. And,
yeah, I mean, super complex, but I also get the impression that sometimes if you take the approach of behavioral economics, it seems kind of an empirical one when you have a pretty simple model of what people behave, right? Because maybe they're not looking complicate optimality, they're just try to say maybe with some empirical calibrated distribution what people will do, right?
Sure.
No, I guess really our idea is to think of modeling the behavior of a manager infrastructure system, and in that case, of course, we hope that they're looking for optimality. But I don't know. I guess that depends on the context. Maybe a relatively simple model of the behavior may be appropriate. Again, our focus is try to understand what is the attitude towards information, but of course, it's embedded in decision making, but is pretty specific for us.
But there, the competing systems might come into the picture, right? Because these different assumptions will make the game rules or the game outcomes differ significantly. So I think this is where the competing systems actually might be interesting as a means to capture some of these aspects. And then there's another thing that Eleni, you mentioned, these performances of, for instance, the monitoring equipment into the future and stuff like this. Of course, it has to be taken into account explicitly, and it can be modeled also adequately probabilistically. But the analysis, in my perspective, let's say using traditional approaches, that will be a killer if you want to integrate all this into your Marco decision processes. I think this is going to be a challenge. But I just want to point at the strengths of the probabilistic digital twins. Where we, in fact, that we use all the knowledge we have about the entirety of the system, including, of course, the performances of the monitoring devices and the control devices which are checking up on the monitoring devices or the operations involving people who are involved in that. So everything just has to be there. And the relevance of their presence in the modeling will come out as a result on their effect on the optimality. But then you might say, okay, but how can we then model this, and how can we analyze this? And this is where I'm saying that the probabilistic digital twins, which we can use to generate outcomes of the reality as we are able to understand it, is actually a really strong tool. Because the scenarios which actually matter, they will come out, and the unlikely scenarios, they won't. And only, let's say, scenarios with a certain effect on the expected value over time will really matter for the decision making. So it is a very it is a little bit a shortcut around the problem of these very, very detailed and complex probabilistic models which have to be solved somehow.
I agree.
And I think we are all looking into this right now from all corners, and it's going to be fun to see what will evolve. But I think the future is going to look a bit different. I think that these technological developments, this new perspective, is going to help a great deal to make things more real and more applicable.
This is a positive statement for sure. No, go ahead. Sorry for the interruption.
I actually, maybe we can also let the other panelists ask questions, but maybe just because we talked about the two-player situation, and then even without the two-player situation, but when you have regulations, as you showed, Matteo, you can have this issue of information avoidance, and in the end, I guess what your type of models and analysis can do is to come up with the recommendations for better policies. So how do you actually make regulations that they do not lead to information avoidance? And I have my own experiences of information avoidance. Some years ago, we were reconstructing our apartment. There had to be a load-bearing wall taken out. So the architect and the contractor were somehow discussing it, and they asked me, "Do you want to know the details?" And like, no, I don't want to know anything, because I'm a civil engineer. I might go to court if something happens. So I better, if I know nothing.
Yeah.
So
exactly. I got very similar anecdote here, very similar. And
anyway, how do you make it
make sense, right? Right. Right. I don't know. I think honestly that it is a very nice, also intellectual challenge, but I don't think that I am, I'm able to solve many problems in the world, including this, right? So on one hand, one can say, well, it comes because people are greedy and they're not aligned with society regulation. In some sense, society is a very good father that knows what is good for everybody, but we are greedy bastards, that we have our interest. And so one can say, if somebody could even say, if the school was better and better in creating more kind of enlightened citizens that are altruistic and in line with society, then, because if everybody has exactly the same utility, this problem will disappear, right? So going in another direction, what we propose on the capitalistic side in the paper, but I don't think was really necessarily, able to have a, well, I can't say that it is that necessarily so effective, is to go in the opposite direction, to say, no, instead of having a rule-based regulation, let's make people pay, penalties because of failures, or let's give them incentives for repairing, so that to create a mechanism that will kind of artificially align the utility of everyone to that of society. So you're a society, you know what are the utility of your children, and you give them the right kind of stick and carrot to have, but in terms of money, just maybe changing their utility so that again, they will align to yours. But reflecting to examples as those that you also told me, I don't know, is somebody would need to really to better understand why the law works as it does. Why we think that if somebody does not know, is is more innocent in some sense. We can't put somebody in jail because this guy didn't know. And I think that, so on one hand, I can understand why it make also perfect sense to me that the laws works as it is with this kind of threshold. And thresholds, they are also very practical, right? Because if we start giving fines or benefits, that will create a lot of problems. So I think that the entire problem is hugely complicated. I'm not an expert in law. I guess maybe Professor Faber, for example, maybe have a much better vision of what is the essence of relativity-based regulation, why we just say, maybe buildings must be safe exactly at this level and so on. So, but I think it is very complicated, and maybe, it would be a bit pretentious for me to think that I can really solve, something so important in the world. I just think that for me, it's very important trying to clarify what the issue is and what are the different effects. That's for me, for now, is enough, up to tenure at least.
Maybe you are too modest.
Yeah.
I see that. Michael,
the only thing I have to, or I could add to this, Matteo, is that the law systems, we have fundamentally two types of law systems in the world. And as I understand it, the British American branch of law, it's not possible. It's not possible to make, let's say, to incorporate risks. The way I remember, I'm trying to recollect, is that everything has to be based on the outcome of decisions and not the prospect of outcome of decisions. But nevertheless, I do think that risk sharing, like when you engage into agreements or contracts, that the risk, let's say, risk sharing in accordance with best available knowledge is the only way ahead, right? And society is losing resources which we cannot lose. We cannot afford to lose. This is the main issue. So it's not a matter of do we like, let's say, risk sharing? Do we think it's a good concept? In my perspective, it's a necessity if we want to be sharp on consumption of resources and improving welfare for the most. So it's just something which has to be there. I also have this small anecdote from not more than 5 days old. I was talking to the group who are in charge of managing the safety in the standardization in Denmark last week, and one of the engineers there, he mentioned that in the office, in the industry company where he's working, they are not allowed to go on any of the construction sites which they have been involved in designing the structures of. They're not allowed to do that. Because if they do, and something is not right, which they don't notice or whatever, they are just pulling in responsibility. Now, I think, as I said, the necessity for sustainable developments is one side, but I also think that a codex in the industry would be adequate, and that is that nobody acts against better knowledge. I think we need this just so that people they know that they're on safe ground if they report back on any issue which looks strange.
Maybe.
Sorry, go ahead.
No, I was going to slightly switch the topic, but based on what was mentioned earlier, that physics-based models are also something to exploit, and of course, we need to have digital twins that are of a stochastic or probabilistic nature. But the question would be, how generalizable do you envision these twins to be? And depending on the application, it's easier to imagine this for wind turbine structures that are often replicas, especially within the same wind farm, for turbofan engines, which are also replicas, but maybe not so easy to imagine for buildings or bridge structures, for instance. Do you think there is potential to these sort of generalizations for the digital representations? I think
absolutely.
So many researchers try to do this with transfer learning, but again, more challenges exist in structural typologies than other.
If you take the perspective, Eleni, that it's not only data driven, that it's also, let's say, driven with a certain level of strength in the priors, right? It's not that we are on bare ground, but we should utilize the data. Then it's absolutely doable. I mean, we do it on a daily practice, right? So when we do large-scale earthquake risk assessments, we categorize whatever is being built into something which can be generically adapted to the individuals.
This is true, but this is one of the examples where it's a bit tricky because we generalize with single degree of freedom representations, for instance, for city-scale effects of earthquakes. And monitoring is not as compatible with a single degree of freedom representation, for example. So we would need something in between, likely for.
Yeah, we would need something which is adequate. I totally agree.
I might quickly suggest that one of the challenges a digital twin is of course defined by its function, right? Whatever you're asking the digital twin to do, and if it is predictive which I guess most digital twins are, you know, generalizing degradation mechanisms is very hard. And it's very hard to do in a lot of applications because it requires supervised learning. And I can't imagine a lot of times you're going to have access to damaged data. I can't imagine a bridge owner or an aircraft owner letting you crash the plane or the bridge just to get data, right? It's so you're challenged by how you will do it, or you rely on probabilistic empirical models, maybe physics-based knowledge. We're going to touch on this, I think, Maha and I, a little bit next week.
Yes, but the interesting point is that, I guess, yeah, it has to be physics-based, at least to some degree, you know. But the interesting point is that exactly these structures that are not replicas, but you know, these common civil infrastructure type of systems, there the uncertainties are much larger. You know? And I'm sometimes surprised by, when I talk with BIM people, that most of them are pretty deterministic people. They use data and then they use statistical methods, but still their way of thinking is very kind of deterministic. And they end up with the representation that is deterministic. And yeah, the civil engineering structures in real life, you know that it's never exactly like this. And so when you plan and you construct, you account for that, and you have tolerances and so on. But it's not reflected at least in the current BIM models of this type of structures. So, I mean, I'm looking very much forward to your talk also next week. But
yeah, we will.
I think that it seems more challenging to do for us. But I feel that this is something we really have to work on to bring this stochastic representation also for structures where maybe it's more difficult.
Well, it's a matter of capturing the essentials, right? The essentials for the decision making, and I don't think that will be impossible. And of course, it can be improved over time. But capturing what really is essential, I don't think that you need, as I also suggested, the digital twin does not have to be a one-to-one replica on all fractals, only in the corners where it matters. And that we need to explore, because we don't know too much yet.
Good. I think, I mean, we can keep on, of course, talking a bit further, but we might slowly end the official part of this. So maybe we could give the two speakers the opportunity to have a final word. And then everybody who wants can also just stay on and we have an informal chat. But we want to have a final word to everybody.
Well, I think there's a lot what could be said more, but I think this is the presentation of Matteo and a little bit of what I was pointing at. I think the let's say major challenges have been spanned out, and also the possibilities. I think so if I should say something, my recommendation to maybe not to the research environment, because they will be able to formulate their own research questions, but to the industry, to the user side, I would say it's high time to move in and make this make this reality. I would not be afraid to say that we are ready to start engaging and making this almost transformation on the management of the built environment. And of course, we have not solved all the problems, but we are far enough to get going and learn and adapt on the way. If we wait, we will not actually progress, because researchers will come up with this, will come up with that, and this is fine, but we will never be able to deliver anything which is practically usable. So we need to engage with the industry to get the first versions up, to get the prototypes up, to learn, to adapt, to learn what is important. As Eleni said, yeah, but you know, a building structure is hugely complex, and is always different from the one next to it. It's true, but does it matter? We need to understand what matters, and we can only get it out by starting. So I would say it's now the time for let's say IT technology providers and the structural engineering community to get together and make the link and move ahead. We need it.
Yeah, and on my side, I think first it was really a great honor to be in the same session with Professor Faber, and also I think that this series is really great. I think that not only between the speaker of today, but also what I've seen in the last seminars, and of course also the next one, I see a very common vision, because it seems that on both sides of the Atlantic, we have a very similar vision of integrating civil engineering with some sense with tools developed like new devices, but also approaches developed also for in other disciplines. And I think it's really nice for us to work in such a time where the boundaries between different sciences are coming down, and we see so many progresses in many dimensions, from again computers to smart cities to new definition and assessment and improvement of resilience. So I think that this is a great time, and I'm sure that this movement is already changing how civil engineering works, and it will do more in the future.
Thank you very much for the closing statements. I guess we can officially end the formal part of this meetup. Thanks everyone for joining us, and I think we can stay longer for those who are available for more.